This presentation is connected to one other presentation of this morning of Thomas Jalabert about piezoelectric materials. So I will not introduce piezoelectricity, but I will go directly to the main component that that interests us, and this is this composite. This is a composite based on nanowires. So these are zinc oxide nanowires as presented by Thomas this morning. So from those nanowires, we can build what we call composites. So it's a mixture of different materials. So here, in this case, they're immersed into the electric material that could be a polymer. And then we have two electrodes, one at the top and one at the bottom. So how can we exploit this kind of piezoelectric composites? How can we test them? So I will explain with these graphs. So what we can do is to apply, for instance, a pressure on this material. What happened with this piezoelectric material? So imagine you apply a pressure on it. So I can represent it in here. If you put a pressure on this material, so you will deform it, and because of the piezoelectricity, the piezoelectric effect, the nanowires will deform, and then you will have a polarization inside, as I represented here. So basically, you have a positive part, a negative part, and because of that, so you will immediately can measure either charges here or a voltage, a peak of voltage, because of this pressure is very sharp. So basically you measure this, and eventually because you have a positive and negative polarization here, all the charges in the metal, for instance, will flow and will try to compensate this polarization. So eventually this potential will decrease and it becomes zero if you leave this constant pressure. And then if you release the pressure from this device, as I represented here, then the polarization will disappear, and you will measure a peak of voltage, which is inversed, corresponding to the first peak. So this is classical, actually, for all materials, not only the composites. Okay, so what I present today, it's a little bit of simulation, theoretical models, a little bit of experiments on this kind of composites, and why we do simulations to try to understand how they work, try to understand the physics behind, and try to obtain optimization guidelines to optimize these composites. So the simulations that I will show are actually static simulations, and I will only give values of this maximum potential, that is this or this actually in absolute value. Okay, so with that in mind, I will present some simulations, very basic simulations versus experiments, and I will talk mostly about piezoelectric, about the semiconductor properties of these nanowires, because they're actually piezoelectric but also semiconductor. So about doping, I will talk about doping, about surface traps, and how that influence the performance. And that will be connected with the presentation of this morning on PFM results that presented Thomas this morning. And then I will end the presentation. How can you simulate this kind of materials? First thing that you can do is start simple and consider that the materials are dielectric. This is the case of most piezoelectric materials, for instance, PCT or PVDF. So basically, when you deform them, so you obtain the polarization, as I explained before, and you can use this potential either in sensors or energy harvesting, for instance. You can connect the resistance here to the piezoelectric device, and you can make flow current. All right. So that's how we started, considering the nanowires as dielectric, although they're not. But let us see what happens. So you can imagine that simulating billions of nanowires in this kind of composites is difficult. So we simplified the models, and we considered only one nanowire immersed into the dielectric, but with the boundary conditions, because actually we solved this by finite element methods. So you have differential equations boundary conditions, initial conditions. So you can make your models so that this individual cell, it's surrounded by others, by adding symmetry. So as I was saying, no semiconductor properties so far. And then we consider that we apply a pressure, as I explained it before. So with this kind of simple models, we can extract many information. For instance, we can play with the materials of the dielectric that we put on the top. We are using PMMA, which is a polymer, but we can change it. We can put oxides or nitrides, go into something more rigid, for instance. And we can play also with the density of the nanowires, meaning how far are they between each other or how close they are. So what I presented here is a simulation of the potential, piezoelectric potential in function of this density, and also in function of the different materials, the electric materials. So you can see immediately that somewhere there is an optimum for the density of the nanowires that we could fabricate. And then another thing is that if you include more rigid materials at the top here, so you can eventually improve also the performance. Something interesting is that if we simulate a thin film, meaning that it's only zinc oxide here. By the way, yes, so it's zinc oxide. You can see that the composite outperforms this zinc oxide. So only by the structuration and the fact that it's a composite, you can already change the performance and improve it. Now, the thing is that zinc oxide, so all these nanowires we consider as zinc oxide, is a semiconductor, as I mentioned. So it's actually doped in the fabrication, and it's very highly doped. So that means that we are not in this case, as we simulated before, but actually what will happen is that inside of the material you will have free charges, a lot of charges. So when you deform the material, that you have the polarization, these electrons, for instance, if n-doped, will go and screen this positive piezo potential. So basically you will see nothing outside, and thus you will generate no current. So that is kind of an issue. And this kind of behavior was simulated in the past by several groups. So here you have only a single nanowire under pressure, consider only doping, and you can see the potential that is generated. It is very low, in the order of millivolts. And what they found is that this potential is concentrated at the top of the nanowire. So this is 4 micron long. So everything happens here at the top of the nanowire, and it is very small for typical doping concentrations. So we tried to do that in the past. So we include dopings in these nanowires. We surrounded by the polymer again. And what we can obtain is this potential in function of the doping level. So here, in this square, red square, are the typical doping concentrations that we can found in experiments. So this is negative, but consider it as absolute value. So you can see that in this range of experiments, the actual potential that you can obtain is 0. So you can tell me, well, it's useless, this composite. But well, actually, there are many groups working experimentally in this kind of devices, in this kind of composites. What's interesting is that the nanowires you can integrate it in many substrates, in rigid substrates like silicon, but also in polymers like PDMS or plastics and even paper. So there is a lot of perspectives in terms of integration. But if you take a look at these red numbers, this is the potential that they reported. So the potential obtained from these kind of devices ranges from tens of millivolts, hundreds of millivolts, even tens of volts. So actually, they work quite well. So, but if we don't understand how they work, then we cannot really optimize them. So how can we explain this, that these devices work? So in our simulations, we included something that was missing before. It's surface traps. So we will see what is this. So this is classical, typical in semiconductors. So it's present in all semiconductors at the surface of the semiconductor. So it's present in thin films, in nanowires, etc. So what is the origin of the surface traps? It's because of that the surface is not as good as the bulk. I try to explain it with this energy band diagram. So because of this crystallinity that is different, it's because of the presence of oxygen molecules at the surface. This is in particular the case in zinc oxide. So you have these molecules at the surface and that will capture electrons. So basically what you have is a charged surface. So if it's charged, so you will have a band bending near the surface of the semiconductor. And because of this band bending, you will deplete. There is a depletion zone, which means that there is no free carriers in this region. There is another effect that is the Fermi level that you can see here. It's changed compared to the bulk, and it's pinned to a different value. So this is what we call surface Fermi level pinning. All right, I will not go into the details about the equations, but we can calculate the surface charge and put it into the model, all right, as a boundary conditions with some hypotheses about the density of these traps that capture electrons. So I want to show you what happens then. So if we put these surface charges or these surface traps around the nanowire, so you will have a depletion zone from the top and from the borders. So I represented in these images. So here you have 3 doping levels: low doping, medium doping, high doping level, that actually corresponds to this red square that I showed you before. All right. So what I show you is the potential. This is the distribution of the potential. This is the distribution of electrons, of charges, in the 3 cases, basically. So for low doping concentrations, the nanowire is fully depleted, meaning that there is no free electrons. So there will be no screening, and you can obtain the maximum potential from the device. As long as you increase the doping level, so you will start seeing a neutral zone, meaning that you have free electrons inside, and that will reduce overall the potential. And eventually for high doping levels, you cannot control this anymore, and you will have, again, a very low potential from the device. So actually what I show here is because of these traps that we added, we can exploit higher doping levels compared to previous models. So this could explain why these devices actually work. But now, on reality, the surface traps depends on many things, in particular on how you fabricate the nanowires. And there are many techniques to fabricate them. There are vapor phase deposition techniques, wet chemistry techniques. And in this graph, you can see that all of these techniques have different doping levels, produce nanowires with different doping levels, and also different density of traps. So what we have done in the recent research is to include these doping levels and these real values of traps to see what is the effect on the real devices. So here I show you just one example, considering thermal evaporation. So you have the values of doping and surface traps. And in this case, we fix the length of the nanowires to a certain value, and we will play with the radius. So I show you the potential here that is produced under compression all the time in function of the radius. So the blue curve is for low values of doping in this range, and the red curve is for high values of doping levels. So if we take a look at the right part of the curve, that means you have nanowires that are quite wide. You can see that the potential is again very low. So for wide nanowires, you always have a neutral region, meaning that you will screen the potential. But then as you reduce the radius of the nanowires to a certain value, we call it critical, so you will obtain the best performance, meaning that, as I showed you before, you will obtain depleted nanowires and you can obtain the maximum potential. So this is a critical value that you need to fabricate the nanowires. But again, if you increase the doping concentration, it will become more difficult to deplete the nanowires. So you need a lot thinner nanowires to do this. So this gives us an idea of some optimization that we can do in function of the doping level and the surface traps. Now, if we compare again the thin film, which include surface traps as well, and the composite, including surface traps and doping, you can see the comparison in this curve. So this is the potential, again, in function of the doping concentration, and the black curve is the zinc oxide thin film, and the red one is the composite. So you can see that in this range of doping concentration, the nanocomposite could outperform, again, the thin film. And all of this is for the same thickness of 2 microns. And now, how this is linked to the presentation of this morning. So this morning, Thomas presented some results of piezoelectric for microscopy. This is not composites, right? This is only characterizations on thin films and on nanowires. But what he showed this morning is that in the thin films, what we have measured, or our colleagues measured, what the thin films have a low piezoelectric coefficient compared to the nanowires that has a higher, about, I don't know, 2-3 times higher piezoelectric coefficients. So the effect of the traps, the surface traps, could explain also this increase in the performance of thin films, of nanowires compared to the thin films. So I arrived to the conclusions. So I hope I convinced you that the surface traps and this Fermi level pinning could explain the high performance reported in experiments of composites, but also could explain recent results on piezoelectric for microscopy. Then all these models gave us important optimization guidelines that could be used for sensors or energy transducers in general. For instance, the nanocomposite performance depends on the growth method of the nanowires, and in general on the length and the radius. I didn't show you results of the length, but you can believe me, length is also important, and it is better to use long and thin nanowires in general. And it is important also to control the doping and the surface traps in the future. And then overall, piezoelectric composites based on nanowires could outperform piezoelectric thin films. Okay, thank you very much for your attention.